Welcome to this lecture on compact objects, the final remnants of stars. In previous lectures, we explored how stars are born, evolve, and eventually exhaust their nuclear fuel. In this lecture, we focus on what happens after a star dies. We will uncover how nature creates some of the most extreme objects in the universe: white dwarfs, neutron stars, and black holes. When a star exhausts its nuclear fuel, it cannot sustain fusion reactions anymore. At this stage, gravity dominates and the core collapses. Depending on the mass of the star, three possible remnants can form: a white dwarf, for low to medium mass stars; a neutron star, for more massive stars; or a black hole, for extremely massive stars. Thus, stellar mass determines the final outcome of stellar evolution. To understand how these remnants resist collapse, we need to introduce degeneracy pressure. This pressure arises from quantum mechanics, specifically the Pauli exclusion principle, which states that no two identical fermions can occupy the same quantum state. In white dwarfs, electron degeneracy pressure resists gravitational collapse. In neutron stars, neutron degeneracy pressure plays this role. Unlike thermal pressure, degeneracy pressure does not depend on temperature. It acts as a fundamental quantum barrier against collapse. A white dwarf is the final state of a low to medium mass star, like our Sun. It no longer undergoes nuclear fusion and is supported entirely by electron degeneracy pressure. Despite having a mass comparable to the Sun, it is compressed into a size similar to Earth. This makes it extremely dense. Over billions of years, a white dwarf slowly cools and fades. It represents the ultimate fate of most stars in the universe. There is, however, a limit to how much mass a white dwarf can support. This is known as the Chandrasekhar Limit, approximately 1.4 times the mass of the Sun. Beyond this limit, electron degeneracy pressure is no longer sufficient to counter gravity. The star becomes unstable and undergoes further collapse. This collapse leads to the formation of either a neutron star or a black hole. This limit is a cornerstone concept in stellar evolution and supernova physics. When the mass exceeds the Chandrasekhar limit, electron degeneracy pressure fails. The core collapses rapidly under gravity. Two outcomes are possible. If the mass is moderate, the collapse halts due to neutron degeneracy pressure, forming a neutron star. If the mass is extremely high, collapse continues indefinitely, leading to a black hole. Thus, crossing this limit marks a critical transition in stellar death. A neutron star is formed from the collapsed core of a massive star. It typically has a mass between 1.4 and 2.5 times that of the Sun, but is only about 20 kilometers in diameter. This makes it one of the densest objects in the universe. A teaspoon of neutron star material would weigh billions of tons on Earth. Neutron stars also rotate extremely rapidly and possess intense magnetic fields. They are supported by neutron degeneracy pressure. Some neutron stars are observed as pulsars. These are highly magnetized, rapidly rotating neutron stars. They emit beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space like a lighthouse. If aligned with Earth, we detect periodic pulses of radiation. Pulsars provide precise cosmic clocks and are crucial tools in astrophysics. When the core mass is extremely large, even neutron degeneracy pressure cannot stop collapse. This leads to the formation of a black hole. A black hole has gravity so strong that not even light can escape. At its center lies a singularity, where density becomes infinite and known physics breaks down. Black holes can also produce powerful jets and influence surrounding matter dramatically. They represent the most extreme outcome of stellar evolution. The boundary of a black hole is called the event horizon. Once an object crosses this boundary, it cannot return. The size of this boundary is defined by the Schwarzschild radius, which depends only on the mass of the black hole. This radius marks the point of no return. Beyond this, escape velocity exceeds the speed of light. Let us compare the three compact objects. White dwarfs are Earth-sized and supported by electron degeneracy pressure. Neutron stars are much smaller, around 20 kilometers, and supported by neutron degeneracy pressure. Black holes have no solid surface, their defining feature is the event horizon, governed purely by gravity. Mass increases from white dwarf to neutron star to black hole, and so does gravitational intensity. Thus, compact objects represent a hierarchy of extreme physics. In summary, the life of a star does not end quietly. It transforms into one of the most fascinating objects in the universe. From white dwarfs to neutron stars to black holes, these remnants reveal the deep interplay between gravity and quantum physics. Understanding them is key to understanding the universe itself.